you know, I need to make sure that I make the correction, that the mistake I made is known to all of you. And I will tell you how I'm going to compensate you for that mistake I made. So let's look at the quiz, which is quiz number 3. Okay, I sent it to you guys, the corrections yesterday and the typo, but these two facts are very, very important, and it was very unfortunate that I overlooked that mistake. So let's look at the mistake. Okay, so do you guys see the screen? Okay.
Yes.
All right, quiz number 3, the third question. So we understand, of course, this question now is being corrected. It's being corrected. The correct answer would be A, B, C, E. Okay, but what I like to emphasize here is that, like I said in the notes, I said if there's no 3 here, right? If there's a 3, x raised to the power 3, taken cubic root, that's equals to x. But if there's not cubic root, it's just a square root by default, this is not going to be equals to x. That would be a mistake. Okay, so this is the correction I will make. And I apologize for the mistake, but I want this to be to not interfere with your study and have the wrong conception, and don't make the same mistake again. It was just merely a typo from my part. Okay, but this question is worth 4 points. It's worth 4 points. So I went into your grade book, and some of you actually got all 10 points in that case. And forgive me, you're not going to get more points, right? You probably have made you made the choice of A, B, C, E. You may not have noticed that this is a cubic root. This should be cubic root, and the cubic root was not present. So you might have overlooked that. But in any case, I just want to clarify. Okay, so this is correct. The version you did at the time you did the quiz was incorrect. It was this version. Okay, so that was a mistake. But anyway, without further ado, so for those of you who have less than 10 points, and I will add certain number of points, I will add a maximum of 4 points to your record by manually. So you will get the credit. So I will do that at the end of the day today. And so that's one thing, first thing I'd like to clarify. Okay. Any questions? And I acknowledge the person, I forgot who that was, Alexa, was it Alexa? Yesterday, that pointed out that mistake. Yes, I did make that mistake, and I apologize. And I appreciate that you pointed out. Thank you so much. Mm-hmm. Who was that?
So, me, Gata.
Okay.
You see,
Hold on.
so on quiz 3, if you got 10 points, you're gonna lose 4 points.
I will have to see each individual's quiz.
Oh, okay.
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 So I will give credit to people maximum 4 points. But if you already get 4 points, you already get 10 points, then I will not be adding more.
Oh, so you want like minus 4 points or anything?
I'm sorry?
I thought you were gonna like deduce 4 points from.
I'm not going to minus any point from anybody.
Okay, okay.
It's just that some people already have 10 points.
Okay.
They made the choice, but it's a wrong choice.
Okay.
Okay, it's a wrong choice, but I still will give that credit to the person. But I'm not going to give that person 14 points. You know what I mean? I was just giving that, whoever got 10 points already, you need to understand the choice you made is the wrong choice under the circumstances, but it's a correct choice after the correction. Is that clear? So So after the correction, the correct choice is this one. It's A, B, C, E. Okay. Well, when I was making up that question, I just simply didn't see that cubic root was missing. Okay, so that was the intention. That was my mistake. Okay, so but when I make the correct choices is A, B, C, E, or A, B, C, E, they're all correct except the D. But it with the mistake there, with if this were replaced by root x raised to the power 3 equals to x, and D would be wrong. So ABC would be the right choice, but ABC was not designated as the right choice. So there's a little messed up there, but that will be. But I want to the bottom line. I want to clarify what is right, what is wrong. Points, I'll compensate you for the points, but you need to know which one is right, which one is wrong. Okay. All right. So I hope that's clear, and thank you very much. And let's move forward. Let's see what's on chat. Yes, thank you for correcting, Professor, of course. And in math, right is right, wrong is wrong. I cannot make right wrong, I cannot make wrong right, right? So I just, as soon as I recognize there's a mistake, I just admit it and correct it right away. That's the attitude, that's the attitude. And there's no hard feelings. It's just, don't take it personal, because math is about a truth and fact. It's about eternal truth and fact, about numbers, of course, about numbers. We're not talking about facts, whatever truths people think of in other fields, but we talk about just in the fields of numbers. We true is true, false is false. Okay, so without further ado, so let's move forward to our lecture. Okay, so today is it's the 8th, right? Today is the 8th. So let me say that as the 8th. Do you guys have any questions from your homework? Any questions on homework? No? Okay, this is right, this is wrong. Okay, if you have any questions, so please let me know. All right. Yesterday we talked about we continue to summarize the 8 basic functions. And I remade the table and I sent it to you. And I hope that helps. But I have to make the table entirely because it doesn't print well. When I try to make a PDF file, it just doesn't print right. So I just entirely, twisted the table, which caused the delay. And but I think everybody should get it on the same day. And today we're going to introduce, and we're going to still be focusing on these 8 functions, but we're going to introduce 2 other concepts. Okay, these 2 other concepts are also very important in your calculus study, in particular in chapter 4. But here, the reason we introduce these concepts is because you're going to encounter them for sure. Okay, so knowing them a little bit earlier, especially we're studying these functions, which has relevant concept, right? We have relevant concepts. So one-to-one function. So can you guys refresh me? What is a one-to-one function? Do you still remember what is a one-to-one function? So we have function, right? We have function. That's a definition of function. And then we introduced the one-to-one function, right? We introduced one-to-one function. A function is called one-to-one, and we talk about to be, not to be, right? One-to-one function. And today we're going to talk about increasing function and decreasing function, right? We want you to practice using the words from the perspective of function. Okay, hopefully this training will help you to get used to the environment of study in calculus. Okay, so that's the main intention. And on top of that, these concepts will also be used intensively in your next class, because at the entry of your Math 190 class is going to be function. Okay, and there's some one-to-one function, and there's some increasing function, decreasing function addressed. We're not going to address the calculus contents, but we address the method of study as related to definition. So the first one is we're going to talk about is increasing function. Okay, what is the definition of increasing function? You guys should have that on second page of the notes. Okay, on the second page of the notes. Okay, so if you haven't put that on your flashcards, please do so. Or put it on your notes, just write it down. Okay, it says a function is called an increasing function okay, a function is called an increasing function on an interval. On an interval. Okay, so we're going to give a name of the interval. We call it I. I is the first letter of interval, right? You see, when we choose the symbols for our shorthand notation, we typically choose the first letter of a word. Okay, that's very typical of mathematics, right? For constant, we choose C for constant, right? We choose C for constant. Function, F, right, is the first word, the first letter of function. So anyway, a function is called an increasing function if, okay, if the output, okay, so I'm going to insert this symbol here, F. A function F is called an increasing function if F sub x1 is less than F sub x2, whenever x1, x sub 1 is less than x sub 2. Oops. In the interval. In the interval I. Okay. In the interval I. Okay. That's the definition of increasing function. What does it mean? First of all, you can see, if you look at the two definitions, word for word, do we see there's a difference? What's the difference in the address interval? In the one-to-one function definition, it's on the entire domain. But for increasing function, it's on an interval. An interval for that function is basically part of the domain. Part of the domain. Okay. So if for that part of the domain, okay, whenever one input is smaller than the other one, and their respective output will also have the same relationship. Okay, so I'm going to take the example. I'm going to take an example to illustrate this. Okay, so I want you to pay attention to what I do with the wording. Okay, what I do with the wording. Now, in the example of this function, which is called f of x, right? We have studied this function extensively, right? And I assure you, a mastery of this function could ensure, okay, mastery of this function and its variations. We will talk about its variations in the future. Could ensure you to get about 20 points plus in your calculus class. Okay, not only just in calculus 1, it could be in calculus 2. Okay, now on this curve, right? We understand it's a function, right? It's a function. So on function, we have a set of, we have input, we have output, right? The input are X, output are Y. And when we translate that process into this curve, what does it mean for the requirement for an increasing function, which is whenever one input is less than the other on an interval. So it doesn't have to be in the entire domain. For example, in this case, right? In this case of our consideration, right? We could look at the interval from 0 to infinity. 0 to infinity. Right? This piece. Input. Whenever input 1 is less than input 2. So I'm going to choose arbitrarily two numbers, x1 and x2. So what are x1? What are x2? x1 is the horizontal measurement. The input is a horizontal measurement from the origin. x2 is the horizontal measurement from the origin. You can see all the inputs are measured in the same way. From the origin, sometimes to the right, if it's positive numbers, and sometimes it's to the left, right? So you can see in this case, x1 is indeed, right, less than x2. X sub 1 is less than x sub 2 in the following picture. Okay, now for x1 less than x2. And what happened to the output? What happened to the output? The output for x1, we're going to draw the vertical line. Remember vertical line test, right? Vertical line. Oops, I need to change the color for better observation, okay? And the output for x1 is the vertical measurement from the origin. Okay, so this height is f of x1. Okay, this height is f of x1. Okay, so I'm going to write it down, this height. This is f of x1. Input, output, because that's how the graph is made after all, right? And what is f of x2? F of x2 will be the consequence of drawing a vertical line. Okay, I know this thing, some of you it's been familiar, but I want to go back to the basics. Okay, these are the basics. And this height is f of x2. Do you guys follow me? For input x1, I'm sorry. For input x1, okay, for input x1, we have output f of x1. For input x2, we have output f of x2. Do you guys follow me? Input, output. So this is how we read the graph, really. Always. Never change. It will not change for you for very long time, unless you decide to go to graduate school, to study mathematics. That might change, there'll be more dimensions, Okay, in calculus 3, you're going to do 2 dimensions. But in most of our situation, it's going to be 2 dimensions. In most of our situation will be in 2 dimensions. So this statement, it says whenever x1 is less than x2, f of x1 is less than f of x2. So we're talking about one is vertical and the other one is horizontal. The input is horizontal, the output is vertical. And in this case, it's obvious, right? But for And we need to require this not just for two of them, it's for any. Any is the keyword, and for any has the same meaning of whenever. Whenever, in other words, you arbitrarily, right? You can also use these words. For arbitrarily chosen x1 less than x2. So these are the wordings you can use, but you can see it's true for any two. That's the key. If you change any to some, then that's not true. That will not work. Okay, it has to work for all of them in that same situation. Okay, so this is the different wording you can use. Okay, but because for any x1, x2 in that interval, right? So in that interval, I, right? For any x1, x2, f of x1 less than f of x2. And you can see the picture, the meaning on the picture, that's what it means. Okay, when one input is less than the other input, and their output also bear the same relationship in size. Is that clear? That's the meaning of increasing function. So now let's look at decreasing function. Are you guys ready? Is this pretty straightforward? Is this guy pretty straightforward? Am I too slow or am I too fast? Hello, guys. Am I too fast or I'm too slow? No comments. Good pace. Okay, good pace. Thank you. Okay, tell me, please, if I'm too slow, it's kind of boring, right? Okay. I'm going slower intentionally because these concepts are very important, and the method of study and the wording and stuff, it's tricky. A lot of people just don't get it at the beginning. But once you get the hang of it, you know how to do it, and you will totally at an advantage. You're not gonna stop getting points. You're not gonna stop getting points instead of losing points. Okay. All right. So this is the increasing function. So from what we did, okay, because, right, you can use this piece, you can use this piece, and you can use whenever. Okay, whenever this happens, therefore, we can say, we can draw the conclusion. We can draw the conclusion, okay? And what can we do? I'm gonna remove this one, just for now. You guys write it down, right? Did you write it down? Because I want to fit it. If I move, it's gonna change the things. I'm gonna cut this. Then you say thus f of x, right? F of x equals to absolute value of x is an increasing function on the interval. You have to tell the reader what it is and where. You have to tell the reader what it is and where to get full credit. Because the definition says so. The definition says increasing on an interval. So when you write it down, you have to say, this is increasing on this interval. Well, then you say, what if it's increasing on the entire number line? Sure, then you say it's increasing on the number line. You know what I mean? So you not only tell me to tell the reader, tell your future professor or telling me it's increasing. You have to tell them where, because if you're missing this word, you're wrong. Why you're wrong? Because f of x is decreasing here, increasing there. And you say it's increasing. Because you didn't specify the interval, so we assume you're saying the function is increasing on the entire interval, on the entire number line. That's obviously wrong. Do you guys follow me? So this is the kind of rigorous words you have to use properly when you are conducting your mathematical courses. Okay, so now, so we got it increasing, right? You in your description, you have the reason. In the reason, you can pretty much see we are citing the definition. We're really citing the definition. In a lot of the situation in your calculus class studies, you're citing the definition with some variations. Okay, you have to just make sure the statement you make is fitting to the definition, therefore you can make certain claim. Okay, anyway, so that's increasing function. Let's see what's the definition of a decreasing function. Okay, let's see what's the definition of a decreasing function. Okay, so I'm going to clean this up. Okay, what's the definition of a decreasing function? Right, from increasing function to decreasing function. Okay, I'm gonna copy and paste, and then I'm gonna change a few words. Okay, a function is called a decreasing function on an interval if, and this is reversed. This is reversed. So your input one is less than the other, but the output is reversed in size. Okay, but how do we describe that? And this should be a pretty straightforward description. For example, this is x1. This is x1 less. Hold on. I'm not very good at drawing these lines very straight, but I must. Okay, so this is x1. No, this should be x2. Okay, this should be x2. Okay, so this is x2 because I want to express whenever x1 is less than x2. So x1 is less than x2, and this is my x2. And I want to form a description that x1 is less than x2. So what's my x1? My x1 is going to be here. Okay, this is something we need to get used to. X1 is here, and I'm sorry, x2 is here, x1 is here. I hope I didn't confuse anybody. Did I confuse anybody?
Is this definition for a decreasing function?
Correct.
Oh, okay, because it says increasing.
Oh, sorry. You see, I didn't change that word. Decreasing function. Thank you. Decreasing function. Okay, decreasing function. So everything's being changed except the title, right? So now I just changed it. Thank you for reminding me. Okay, x1 is measured from the origin horizontal. x2 is measured from the origin horizontal. So input is measured horizontally from the origin. That number line, okay, from the origin. And what's their output? What's their output? Right, so I'm going to draw the output. Okay, if you have any confusions or because I may make mistakes, right? So this is the output for f of x1, and this is the output for x2. And the output is measured vertically from the origin. Okay, from the origin. So now let's write the notation. This notation, because that's the input is x2, so the red is f of x2. And this other one is f of x1. Let's look at if the situation we have here is fitting for whenever x1 is less than x2. x1 is less than x2. Do you agree? Even though x1 looks longer, but they're both negative numbers, aren't they? Right? So x1 is indeed less than x2. So whenever x1 is less than x2 in that interval, so we're going to specify that interval. What will that interval be? This time the interval is going to be from negative infinity to 0. Okay, so you can say on that interval or in that interval, whenever x1, x2 are in that relationship, okay? Because they're both negative numbers. The absolute value, because we're considering this absolute value, right? Is this true? Well, you can see the output is reversed, right? F of x1 is higher than f of x2 because they're both positive. They're above x-axis. They're above x-axis, okay? And then you would say, yes, okay. The absolute value of x sub 1 is larger than the absolute value of x sub 2. Whoops, sorry. Okay, x sub 2. Is that a true statement? Is that a true statement? If that makes a true statement, right? Remember, you need to think about all the possible numbers. On your mind, you might be checking. On your scratch paper, you might be checking. -5 is less than -2. But the absolute value of -5 is larger than the absolute value of -2. Do you follow me? Right? You may think about these concrete numbers, but in your statement, you have to write it this way. Do you follow me? Yes? And then you would say, thus, or therefore, f of x, right, this guy, is a decreasing function on the interval of -∞, 0. So you not only need to tell the reader what it is, and also need to tell the reader each specific symbols and where they are. Okay, so in summary, right? In summary, I'm gonna have to clean this up. Do you guys see this, right? You got this. Yes? Any questions? Can you please explain how to get x1, x2 for the decreasing graph again? We choose them arbitrarily. Okay, we choose them arbitrarily because the word whenever. Okay, they are arbitrarily chosen. We just have to guarantee whenever x1 is less than x2. So our situation is x2, okay, x2, okay, this is x2, and this is x1. x1 has to be smaller, right? x2, x1. You need to make sure whenever, because you're going to examine if that statement true. If that statement is true, then it is a decreasing function. If the statement is not true, it's not a decreasing function. Got it? In other words, if for some x1, x2, x1 is less than x2, but f of x1 is not greater than f of x2, then it's not a decreasing function, which is less than equal to. In this situation, the situation can be a little bit more complicated in our discussion, but I don't think I want to get into that direction because it's going to take a lot more time. But I think this much is enough so far. If you think more, and I welcome you thinking more, and get back to me and we can discuss. Okay, but do you get this part? You get this part. So in summary, right? In summary, I can do this. I can say this, right? F of x is increasing on the interval of 0, to infinity, decreasing on the other interval. So this is the kind of languages you're going to be using. Okay, this is how specific you need to be. This is how specific you need to be. Okay, so do you get it, Hazel? Yes, you got 2 colors in your name. I read each one of you guys' bio. It was very interesting. Okay, it was very interesting. Thank you for sharing that with me. But anyway, you could use bracket. You could use a bracket. It's okay. It works for bracket too. Okay, that's a good point, Carlos. You could use bracket. It works the same way. Okay, but in most of the situations in your calculus setting, we use open interval. We use open interval. Okay, and if you include the 0, that's fine too. That works too. Okay, so that's the definition of increasing function and decreasing function, right? So I'm going to quickly go over these 8 functions we have discussed, right? These 8 functions we have discussed. Is every function increasing or decreasing? Do we have function that's neither increasing nor decreasing? Right? You start to think about these questions because you think about all these possible functions, right? For example, the first one, the constant function. The constant function is neither increasing nor decreasing because they always equal to the same number. The output is always the same number. So this is neither, right? The second function, right? 1 over x, is it increasing or decreasing? Is the summary enough as a standalone answer? Yeah. It just when you talk about increasing function, decreasing function, then what I just summarized is it can be a standalone answer because it depends on what's being asked for. Okay. In your calculus class, you will be learning that you're going to be given a little bit more complicated function, and then you're going to decide when is increasing, when is decreasing, and where the highest point, where is the lowest point, and so on and so forth. Because typically you can see if it goes up and then down, it has a peak, and that's max. When you go down and up, you have a lowest point. The typical of maximize the profit and minimize the cost, and these are the functions that are related to it. And those functions typically have those features. You go up, increasing, and you go down, decreasing. So you have a peak. Okay, it could be local peak, it could be, whatever. So you're going to learn that in calculus class. I'm not going to address that issue, but it's pretty intuitive, right? For example, in the case we have here, right? The curve decreases, goes down, 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 and up, and then it has a lowest point. And this is the minimum, the lowest point, right? Does that make sense? Okay. Now, f of x, is this function increasing or decreasing? Where? Right, so we're going to use a criteria. Right? So let's take the second one, for example. Okay, take the second one, for example. This function, is it increasing or decreasing? Where? On this piece, it decreases, right? Isn't it? Because if you, as you draw the, you're going to start to use a definition, right? Whenever one input, this input is smaller than the other input, and the output is reversed in size. Okay, the output getting smaller. So this piece is decreasing. How about this piece? Is this piece decreasing? Is this piece decreasing? Is it decreasing?
Would it be yes, because it's going more negative?
Yeah, right. It's getting smaller and smaller, right? So you only consider the value. So both p's are decreasing. So this is a decreasing function. This is a decreasing function, right? It's decreasing on this piece and decreasing on that piece. Make sense? Right, so you start to use the x1, x2 to be concise, all right? So we have different, we have a decreasing function cases. Hold on, I'm going to clear this and let's look at some other functions, okay? So go through these. How about x squared? X squared is similar to absolute value of x, right? On one piece is increasing, on the other piece is decreasing. Now, how about this one? F of x equals to y. This function is increasing on the entire domain. X raised to the power 3, increasing on the entire domain. Okay. Square root of x, increasing on the entire domain, increasing on the entire domain. All right. Okay, so without further ado, now, another common practice is that after all these concepts are introduced, right? I'm going to give you an example here. So now we have increasing function, decreasing function in addition to the one-to-one function. And we want to study the relationship between these concepts, between the concepts. So what are these concepts? One-to-one. Number 2, increasing. Number 3, decreasing. How they are related. We're not going to study every aspect of it, but I want you to study one aspect of it. Is an increasing function one-to-one? So my question is any increasing function one-to-one? Okay, to be more specific, okay, let me put it this way. If a function is increasing on its domain, is it a one-to-one function? Is it a one-to-one function? Right, all kinds of questions you're going to learn, it will be asked in calculus class, right? Is it continuity lead to differentiability? Is it different differentiability lead to continuity, and so on and so forth? So these studies will be there, and so you need to have a little glimpse of these methods, right? This is called critical thinking questions. These are called critical thinking questions. Okay. So if a function is increasing on its domain, is it a one-to-one function? So this is the condition, right? This is the condition. The if part is a condition. And the other part, right, is the conclusion. But we're not sure about it. Not sure about it. In order to do this, we have to look at the definition of an increasing function, right? And compare these two definitions to see which one will cause the next to happen, right? Condition, conclusion. So the definition of increasing function, let me copy and paste here, right? This is the definition of an increasing function, right? And the other one is the definition of a one-to-one function. So we are given, okay? So this is a given, right? So this is a given. Does it lead? Is that a condition lead to that to this conclusion? So you have to speak the language. You have to speak. You have to know how to speak this language. Okay. So I'm going to show you how to do it. If you don't understand it entirely, don't get stressed out. Okay. You're going to be readdress these things in your calculus class, and you still have time to think about it over the semester. And I'll be working with you. And I assure you, this is not going to affect your grades a lot. Okay, it's just a little preliminary exercise to give you a glimpse of the methodology of studying calculus, but it's not going to harm you if you don't get them 100%. Just try to get as much as possible. Okay, now, so what I'm going to do is I'm going to show you the work, right? So knowing the definition, I have these definitions, and then I'm going to show you the work. Okay, and you try to understand as much as you can, ask questions and study afterwards and get back to me if you wish, right? So I'm going to put some notations here for convenience, right? If a function is increasing, right? So when I start, I would say since f is increasing on its domain, right? So I'm going to elaborate what it means to be increasing. Okay, that means whenever x1, x sub 1 is not equals to x sub 2. You see, I did not use x sub 1 less than x sub x2. Why? Because I want to be fitting to the one-to-one function, but I also want to use the increasing function definition. Okay, so I'll show you how I put the wording. Whenever x1 is not equals to x2, we can assume. Why could I assume? Because if x1 and x2 are not the same, I can assume one is less than the other. So assume x sub 1 is less than x sub 2. Right? Because x1 and x2 are not the same, therefore I can assume one less than the other, or I can assume x sub 1 is larger than x sub 2. You know, either way. But if this is the assumption, then, right? Because it is increasing, and I know this is going to be true. Right? Because under that assumption, if f of x1 is less than f of x2, what does that mean? It means they're not the same. So the part that's fitting for one-to-one is which part? Is whenever x1 is not equal to x2, f of x1 is not the same as f of x2. That's all I need to fit the definition here. Do you follow me? You follow me, right? So not equal to is a natural conclusion of less than, right? Because if it's less than, they're not the same. Make sense? I address this because we're going to use this conclusion in the future. There are a lot of other questions we could ask, but I don't want to dive into even deeper, and that will be like doing too much of a calculus class. And you will get a glimpse of it. You just get a glimpse of it. And in your calculus class, you have plenty of time to do it. You have plenty of time to do well on these. So without further ado, what is the conclusion? And this is true. This statement is true. Wait. Okay, this is true. So the question mark will be removed. If a function is an increasing function, is increasing on its domain, it is a one-to-one function. So we're going to get to use this semester. Okay, actually very soon. If it's a one-to-one function, it has inverse, right? If it has a one-to-one function, it has inverse. Now, any questions so far? Okay. So did you write it down? You may like to put a flashcard, put this conclusion on a flashcard. Okay, so here I will give you as a proof. Okay, so let me specify this clearly. This is the proof. So this is a kind of, I wouldn't even call it a theorem, but it's a fact, right? If a function is increasing on its domain, it's 1-to-1. And if a function is decreasing, it's also 1-to-1. Okay, so another one is that statement. So I will combine them as if it's increasing or decreasing on its domain, it's a 1-to-1. And the decreasing part can be proved similarly, but I'm not going to do that in class. So I just give you this glimpse of the method of study in calculus in terms of concept. And so this is the end of proof. End of proof. So this is a fact. Okay, a fact. So far, so good. Everybody in shock? Don't worry too much. Okay, I'll lead you through this. It's just a glimpse of it. It's not going to affect your grade in any way. I give you introduction and make you think. That's all I intend to do here. Okay, and next we're going to continue on the table. Right? So we studied these concepts and we have covered all these concepts up to decreasing function. We still have 2 more definitions to cover, which is even function, odd function. And we will cover those later. And I believe some of you already had them before, but we will review them when we are in trigonometry. Okay, we'll review those concepts when we're in trigonometry. But so let's move forward on table basic 1, and we're gonna get to number 9. Okay, I want you guys to look at number 9, 11, 13. 9, 11, 13. Okay, so move to the top. Basic 1 again. So far, we're building the foundation. Okay, so number 9. The function in consideration is 2 to the power x. 2 to the power x. This is a function. Okay, because this one spells out the rule of the function. And what is the rule of the function? Your input, and this input will be served as a power. So this is the rule. It produces exactly 1 output. And that exactly 1 output is 2 to the power x. Power. So the input served as power produces 2 to the power x. And the base is 2, x is the power. Okay, so I think I will review a little bit about the power operation. Yes, do you guys remember any power operation? Okay, for example, you might have seen something like this, b to the power m multiply b to the power n equals to, what does it equal to? Yeah, what does it equal to? B to the power m. Any idea?
It's b to the power of m plus n.
Very good. Very good. Any other opinions? But because there's only one of you responded, I want to be on the safe side. Okay, I want to just talk about the basics of exponential. Okay, the power. Where did the power come from, right? So we have 2 2 times 2 is 2 squared, right? And 2 times 2 times 2, 3 times is 2 to the power 3. Do we all know that?
Yes.
Yes.
Good. Now we make it more general. Any base, any number as a base, 3 times. Any power, okay, it could be 5 power, right? You see the generalization process? Generalized. So it could be many. So it could be n of them. Do you see that generalization process? That's called a generalization in mathematics. We start from something simple. Okay, so in this operation, you can see because we generalize the process, B is called a base. Right? And N is called power or exponent. Exponent. Now the question is, what is qualified to be the base and what is qualified to be exponent? In general, any number can be. Any number can be the base, any number can be the exponent. However, in the case of division, denominator cannot be 0, right? When did we learn that? We learned that a long time ago, right? Maybe you're at the beginning, you know about numbers, you know the denominator cannot be 0. You probably know why, but I'm not going to dive into that aspect unless you request. Is that denominator cannot be 0 as a fact that we need to observe forever. When we deal with numbers, 0 can never be the denominator. So with that simple observation, we will derive that b to the power m multiply b to the power n is b to the power m plus n. How about b to the power m parentheses? What would that be? It sounded like I'm checking on your memory, and I'm actually not intended to check on your memory. I want you to be able to figure out without having to memorize those formula. Okay, so what's the second one? And let me give you a couple more questions, right? B raised to the power of negative n, right? One, I'm gonna increase the fonts a little bit because you don't see the negative sign. Right, what would this be? Right, and what is b to the power 0? Right, and there are a bunch of other things, right, to the power of n, and there are a bunch of other stuff. If you can fill up all these formula in place, that's great. But better yet, if you know how to use them. Okay, for that reason, I will be assigning you some homework to practice as a review today. Okay, so now, do we recall all of these? If you don't remember, what would you do? Don't worry. If you don't remember, that's not the end of the world. No problem. You can derive it all by yourself. Okay. For the first one, I'm going to start with the first one, which is pretty straightforward, right? We start from some simple case. 2 to the power 5 multiply 2 to the power of 3. What does that mean? That means 2 times 2 times 2 times 2 times 2, 5 times, right? That's the first part. The next part, 2 times 2 times 2, 3 times. So how many times in total? 2 to the power of what? 1, 2, 3, 4, 5, 6, 7, 8. Right? And 8 is 5 plus 3. Right? Do you have to memorize? No, you don't need to memorize. In your mind, you just have that picture. You just have that basic, you just need to have that basic definition. Okay, so this will be true if you choose a B, right? This will be turned into B. Right, see how that works? Do you guys follow me? Am I too slow on this? Yes?
No.
Oh, okay, so what is M? What if this is M, this is N? And that will be, you have M of them, right? We have M of them. M times, right? And over here, we might have N of them. N times. And therefore, this is going to be what? M plus N. Right? Do you need to memorize? No, we don't need to memorize. Okay, so how about dividing? You can derive dividing, right? So forgive me, I'm not going to do it here. And I trust you guys, you know, getting the hang of it, right? Now, how about this guy?
You multiply.
Multiply. Why? There's two layers, right? First layer says the parentheses multiply itself n times. N times, right? So this is a total of n times. N times. And then what? Each one you have m times, right? How many m times you have? N times. So therefore, it's going to be what? B to the power of m times n. Right? Because in each one of these times, you have a m times, right? So total of m times n times, right? So that's pretty straightforward. How about this guy? This one turned out to be one of the hardest one. Okay. So tell me, what do you know about the negative power? How about b raised to the power 0? What is b to the power 0?
Isn't it just 1?
Anything else attached to it? Is there any restriction on anything?
Pretty sure that's just it.
That would be wrong. There is a restriction on this. There is a restriction on this. That restriction is b cannot be 0. So this is wrong and this is right. Why is that restriction so important? And why is this one written into one of the properties? Right? For example, it came from here, b over b. What is b over b equal to? Can't have 0 to the 0 power. 0 to the 0 power is undefined. You're correct. Okay, you're right, Carlos. This equals to 1 under the condition that b cannot be 0. B cannot be, if B is not 0, we can do that, because if it's B is 0, we're dividing by 0, that will be undefined, right? Because of this, we have B raised to the power 0, which apply this property here, equals to 1. That's why this is right and this is wrong. Okay, 0 to the power of 0 is undefined. Whoops. Okay, it's undefined. Okay, it cannot be. So in this case, it doesn't work. So this condition must be attached to it. Okay, this condition must be attached to it. Okay, so that's B to the power 0 equals to 1, provided that B is not 0. Very important. So everything has to be done very rigorously, very rigorously. We're laying the foundation. So now let's look at the negative exponents. Okay. What do we do if you have a negative exponent? For example, okay, I'm going to move down a little bit. In the case of 2 to the power x or b to the power x, right? In these cases, what does it mean if I have 2 to the power -1? Right? So what can be qualified as the exponent? Can the exponent be negative number, be positive number, 0? We know we're good with positive number as the exponent. We're good with 0 as exponent, but sometimes we kind of not quite used to when the power is a negative number, even decimal fraction, right? For example, what do you make of it? 2 to the power of half, right? 3 to the power of 2/3. What is that? Two to the power of 1 is equals to 1 over 2. Okay, or 2 to the power 1. But 2 to the power 1 is 2, therefore this is just half. 2 to the power half. Okay, so the power can be fractions. 2 to the power half will be what? The base is still 2. The 2 goes here. And the power is a fraction. Right? You see, the power is a fraction. In this fraction, there's a numerator, there's a denominator. The numerator is going to go here. The denominator 2 is going to go here. But because this is √2 by default, we just write it as square root of 2. Okay. Now, how about 3 to the power 2/3? Okay, you guys, if you understand, can you write it down on your paper? Anything to the power of 0 is 1. Wrong, but thank you for the contribution. Anything but 0 to the power 0 is 1. That's right. Anything but 0, anything except 0 to the power 0 is 1. Very good wording. Okay, then you just have to go back to you have to go back to re-examine what you said. Okay, anything but 0 or anything except 0 to the power 0 is 1. This will be true. Okay, but this will be false. So do you see the difference? In fact, I think if you're you like to be a speaker or public speaker, and mathematics will train you to be a better speaker. And Christopher raised his hand. Go ahead. Chris?
Oh, no, sorry, I did that by accident.
Oh, no problem, anytime, okay? You know you can ask question anytime though. All right, so what is 3 to the power 2/3? Well, that's how we make it, right? Base 3 goes here. The fraction is the exponent. Okay, in the numerator of the exponent is going to be 2. Denominator goes here. So this guy is really just cubic root of 9. Carlos shared a picture with everybody, so please take a look. Okay, you guys. Thank you for sharing that picture though, but I need to critique this. The 3 is in the wrong place. The 2 is in the wrong place. Okay, the power 3 in the wrong place, the power 2 in the wrong place. You see that? Okay, thank you for your contribution. So let me grab that to show it to everybody. Okay, thank you for sharing that, Carlos. Okay, this will help everybody to understand this concept. Okay, so pronto. Let's see. There. Do you guys see that? You guys see that? You just see that on the screen, right? I'm going to make some corrections here. Thank you, Carlos, for that contribution. Really appreciate it. It gave me the opportunity, right? So first of all, you write the exponents too low. So it looks like 3 times 2/3. Well, 2/3. And that's very confusing. So you should write it 3. The power on the shoulder. Okay, and then the root part, the denominator of the exponents goes here, not here. Okay, and the 3 is the base, this 3 is the base. Okay, the power 2 goes here. Does everybody follow me? So when you write it by hand, your math teachers are very picky about it. Okay, don't ever write the exponents at the same level of the base. Never ever do that, because if you ever do that, it will be confusing and you might lose point. Okay, and you don't want to lose point for such a small thing, right? Okay, I hope that's clear. Thank you for sharing. So let's go back. Right, so when you write this, right, so look at the levels, right? I'm going to show you. You see, the base is at this level with the equal sign. The power is at the next level, higher. Do you see that? Yes? All right. So this must be very clear, and in writing, it's very important. Okay, you may think you're writing as a power, but you have to make that a clear distinction. Okay, the position of numbers in math makes a difference because they have their face value, they have their place value. Okay, so without further ado, so let's go back to more practice. Okay, more practice. So in general, then you say, what if I have 5 raised to the power of 0.25? Could I do that? Of course you can do that. The power can be a decimal number. Okay, but what are you going to do with 0.25? Your calculator probably will produce a number, but in our situation, we typically would like to write it as a fraction, because every decimal can be written as a fraction. So we're going to write it as a fraction. So this is going to be a quarter. So this number will turn out to be the 4th root of 5. Follow me? So the exponential, these are called exponential form, root form, and they have a one-on-one correspondence. And in general, okay, in general, remember the homework I left you guys yesterday? Basic 33. And some of those questions are typical. It could be a typical last step of calculus 2. A lot of our students may not remember how to simplify, but you will typically encounter root 2, root 3. So you need to be able to handle them correctly to get your final 2 points. Okay. But anyway, so in general, if you have a base raised to the power of m over n, okay, or I'm not going to use m over n. I'm going to use something else. I'm going to use something more fun. I'm going to use heart here. I'm going to use a spade. I'm going to make the fonts a little bit larger, okay? Guys, in general, base, power, exponents, sorry, what did I do? Okay, this is the power, okay? So this will be translated into the root form. Will be, you still have the same base here, but the numerator is going to go inside. And the denominator of the exponent is going to go here. Does everybody follow me? So with that said and done, we realize that we can have any real number serve as exponent. So now let's go back to our initial discussion. Go back to our initial discussion about 2 to the power x, right? If this is the rule, what would be the qualified input? What will be the qualified, what will be the consequential output?
From 0 to infinity.
From what?
0.
From 0 to infinity?
Yeah.
So you mean we cannot use negative number?
No, all real numbers.
That's right, all real numbers. So now you see
okay.
it's for real, right? Because the exponent can be negative, positive, 0. All real numbers. And what's the range? That's the question. Okay, so now I want you guys to roll up your sleeves to work with me. Okay, we're gonna make a table. Input, output on this rule. Input, output on this rule. Okay, and then we make points. Input, output. So I'm going to give you a bunch of input. Okay, I'm going to give you a -3 as the input, -2 as the input, -1 as the input. I'm going to give you 0 as the input. I'm going to give you half as the input. And I'm going to give you 1 as the input. Okay, and I'm going to give you just 2 more. Can you fill them up? 2, 3. So now we know how to operate them, right? Let's practice. And I will give you more homework on these practice of using exponents. Okay, so hopefully you'll be prepared in this area. So the rule of the function. The rule of the function, right? Same rule. The same rule produce those functions. So if this is -3, the power is going to be -3. And we're going to assess the value. We're going to produce an output. And what will be the output? Input, output. Input, produce some output for me. Are you guys working on it? Please do. Paths. Sorry. Just give me a sec, okay? I'll be right back. Okay, you work on that table, please. How's it going? So for the input of -3, our output is 1/8, right? For the input of -2, what is our output? is a quarter, right? So my input is -2. Our output is a quarter. Isn't that interesting? The input is positive, the input is negative, the output is positive. Okay, it looks like as the input increases, the output increases too. But these are just anecdotes, right? We cannot draw a general conclusion based on these two stories, two anecdotes. So we need to continue to observe. And 2 to the power -1, we know that's half. So for input of -1, the output is what? Is half. For input equals to 0, 2 to the power 0 is 1. So when input is 0, the output is 1. So far, we only get positive output for negative input and 0. So let's continue to observe. So this is going to be √2. Don't worry too much about the actual value of √2, okay? It's just a number between 1 and 2, okay? And if you plug in calculators about 1.414 something, you know, I don't even remember the exact value. Don't worry about it. Just using √2 is perfect. I assure you that most of you professors just want to see √2. They don't want to see 1.414. I mean, in most of the situation, in most of the, you know, the schools you go to, 4-year schools, and those nerdy, nutty professors, they don't want to see the decimal number. They only want to see those radicals. Okay, if there is one. Now, 2 to the power 1 is 2, right? So now we get 2 other pairs. One is half, one is half the input, and the output is √2. And the next one is half is 1, input is 1, the output is 2. For input is 2, the output is 4, right? So we're doing better than this, right? 3, then 3, 8. So this is a 4, this is 8. We're getting better at this. And then what are we going to do with it? We're going to plot these numbers. We're going to plot these points, input, output, right? So let's do it together. Okay, let's do it together. Did you have your paper pencil with you? Yeah? You have your paper pencil with you. So I'm going to plot these points in place. So you can see how you're going to create your very own analytical geometry pictures. Okay, so the first point, -3, 1/8. So I'm going to make I'm going to put that point in here. I'm going to add a spot, add a point, and make it a little red dot like we used to. A red dot. Okay. Let's see what it is right there. Okay, right there. Okay. The second point. Whoops, what did I do? I have chosen the wrong, I'm making the wrong choice. Huh, what did I do? White, red. I have all these points. Oh. That's why, got it. Why this red line? Okay, that's better. I just removed it. Okay, we didn't need that. So the first point, which is right here, the second point is right here, right? And one by one, we're gonna plot these points. And after 1 is half, input a half, output the √2. And input 1, output 2. Input 2, output 4. Input 3, output 8. So we just plot point by point, one by one. Are you doing it? You're doing it. You can do it, right? Isn't that easy? Very easy. And we connect the dots. And when we connect the dots, what do we see? When we connect the dots, what do we see?
We
a
see
curve.
increasing.
Very good, very observant. We see the increasing, and what else? What else do we see?
We see the range.
We see the range. Interesting. What is the range? We just observed, right? We just observed that all the output are going to be positive. Can you imagine what will be the output for -4 as input? So it looks like in this direction, the curve is getting lower and lower and lower, isn't it? Right? But the question is, so there are two questions here. Is it possible to have 0 as the output? Because if we have 0 as output, the curve will cross the x-axis.
The curve will not cross x.
Very good. The curve will never cross the x-axis, right? Because no matter what is the input, right? For example, if I have an input, okay. If I have an input of -1000, what will be the consequential output? This is going to be -1000, right? So this is going to be 2 to the power -1000. 2 to the power -1000 is going to be a very small number. But yet, it is larger than 0. It is larger than 0. Even though it's going to be a very small number, if you punch in your calculator, you probably you might even get a 0, but it is not 0, okay, guys? It's not going to be 0. It's just going to be a number very close to 0. Then you say, why my calculator give me 0? Because your calculator is limited on precision. Okay, every calculator is limited on precision. And this number definitively is not going to be, if we want to know the value, let's see if this software will give me the value. Okay, give me a numerical value. Very small, you can see, right? It's very, very small. It's going to be like 0.9000000, like over 300 zeros, right? That's what it is. Very small number. So this number is still larger than 0. So no matter what the input, the output is going to be what? No matter what the input, even if the input is -1000, which is way back to the left, it's going to be, the output is going to be larger than 0. So your conclusion is right, but I want you guys to have that imagination in your mind, because this kind of vision can only be seen our mind's eye. The computer actually cannot produce it. Okay, so the output will never be equal to 0. It can get infinitely close to 0, but it will never be 0. Very good. Okay, so now what is the range? Right, so what are the visuals that tell us what the range? We just talk about the vertical height, right? Tell us the range, right? The verticals tell us the range. How high, right? These height tell us the range, right? You can see all of these heights are going to be above x-axis, as large as possible, as close to 0 as possible, but never be 0. Therefore, what is the range? So that's the visual. Sorry, I'm going to. You guys got it, right? Well, actually, our class is over. So I'm going to put that conclusion here. The range is what? What is the range? Negative infinity to positive infinity. Is that right?
That
Is it
was
possible?
domain.
The domain is negative infinity to positive infinity. The range, is it still negative infinity to positive infinity? It will never be less than 0. It will never be equal to 0, right? It should be from what? That's right, Alexa. It should be from 0 to infinity. Okay, and my preferred form is 2 to the power x is larger than 0. This answer is correct, but not going to get you points. This is my preferred form. F of x larger than 0 with f of x clearly specified. That's good. Okay, one sentence. Okay, we're going to conclude the lecture. One sentence, domain and range. Okay, so we're going to describe domain and range in one sentence. Very important sentence. Okay, is 2 to the power x is larger than 0 for any real number x. I want you to write this down and box it. Box it.
Yes.
Okay, you're going to see that we're going to use this statement over and over and over again in many different occasions or something similar. So do you agree with that statement? Do we agree with that statement? Is that truth? Sorry. Why did I do that? Okay, is that truth? This is mathematical truth. This is another piece of mathematical truth. Okay, so all we have done here by plotting the points, getting the graph is to support this statement. They're all supporting each other. They're all supporting each other. Okay, so that's all for today. And I will see you guys tomorrow. Great job, great participation. Give me a little more time for me to process the grade change, and I just give me a little more time. I have lots of things going on in my life right now, so but I will not delay that. I'll try to get it done today. Okay. Thank you so much. I'm looking forward to seeing you guys tomorrow.
Thank you, Professor.
Thank
See you tomorrow.
See you tomorrow.
Thanks for the
Take care.
lesson, Professor.
Thank you. Wonderful contribution and participation. Okay, you can raise your hands anytime, okay?
Professor, we have homework, correct?
Yes.
Okay.
Your homework will be assigned in a minute.